But a poorly built timber floor is a nightmare of squeaks, bounciness, and vibration that can ruin the experience of a building. So, how do you transform a pile of lumber into a stiff, silent, and stable platform? The answer lies in understanding the different systems and the critical engineering principles that make them work. In this video, we're framing up everything you need to know about timber floor construction. We'll move from the traditional joist systems used for centuries to the modern engineered solutions that allow for longer spans and faster installation. By then, you'll be able to design, specify, or inspect a timber floor with confidence, knowing exactly what it takes to build a high-performance floor that will last for generations. Let's start with the foundation of most wood frame construction, the platform frame and its core component, the joist. This is the time-tested method where floor joists, typically dimensional lumber like 2x10s or 2x12s, are spaced at 16 or 24 inches on center and span between load-bearing walls or beams. The joists support a decking layer, historically diagonal plank sheathing but now almost exclusively plywood or oriented strand board OSB subflooring, which is glued and nailed to the joists to create a rigid diaphragm. This diaphragm is key. It doesn't just provide a walking surface. It ties the entire structure together and distributes lateral loads. The maximum span of a solid sawn joist is limited by its depth and the grade and species of the lumber. A pro tip for eliminating the dreaded floor bounce is to use a simple rule of thumb. The depth of the joist in inches should be roughly equal to its span in feet divided by 2. So, for a 16-foot span, you'd want a joist at least 8 inches deep, like a 2x10. A common and costly drafting mistake is to maximize the joist span right to the code limit, which often results in a bouncy floor that meets the legal minimum but fails the comfort test. To overcome the limitations of solid lumber, we have engineered wood products, which are the modern engineer's best friend. The most common of these is the joist. Shaped like a steel I-beam, it has a top and bottom flange made of laminated veneer lumber (OVL) or solid sawn wood, connected by a web of oriented strand board. Third, and often overlooked, the open web allows for easy routing of plumbing, electrical, and hook ducts without the need for drilling and notching that weaken solid joists. The efficient workflow secret is to always follow the manufacturer's specifications for web stiffeners at bearing points and where concentrated loads occur. Another critical engineered product is the open web steel joist or truss joist, which provides even more space for services and is often used in commercial and multifamily projects. CLT is like a giant, structural plywood panel made of multiple layers of dimension lumber glued together at right angles. When used as a floor, it acts as both the structural framing and the finished ceiling below, all in one element. CLT panels are manufactured to precise tolerances off-site and then craned into place, dramatically reducing on-site labor. They offer exceptional fire resistance due to their mass and predictable charring rate, and they provide a beautiful exposed wood ceiling. The primary challenge with CLT is the connections. The panel-to-panel and panel-to-wall details must be meticulously designed to transfer loads, especially in seismic zones. A pro tip for CLT design is to integrate the service routes for electrical sprinklers into the design phase, using CNC-routed chases in the panels to avoid on-site cutting. A timber floor is more than just its structure. Its performance is defined by 3 critical systems: bracing, sound insulation, and fire resistance. Bracing, provided by solid blocking or engineered bridging between joists, prevents the joists from twisting and rolling over under load, which is essential for long-term stability. This is achieved by using resilient channels or a floating floor system, where a secondary layer of subfloor is isolated from the main structure with a resilient underlayment, effectively floating on top. NAS, in the form of acoustic insulation bats between the joists, is also crucial for absorbing airborne sound. For fire resistance, building codes require a specific fire resistance rating for floors between units. This is achieved by protecting the timber with multiple layers of fire-rated gypsum board, which creates a protective thermal barrier that delays the temperature rise of the wood, allowing occupants time to escape and firefighters to respond. To summarize the key takeaways: 1. Traditional joist and platform framing relies on a closely spaced grid and subfloor diaphragm for strength. And 4. The ultimate performance in bracing, soundproofing, and fire resistance is achieved through intentional detailing, not just the primary structure itself. Now I want to hear from you in the comments below. What's the biggest challenge you've faced with a timber floor? Was it eliminating bounce in a long span, achieving a high STC sound transmission class rating for a condo, or integrating massive services through the structure? Your practical experience is invaluable. If this guide to timber floor construction has provided a solid foundation for your knowledge, please give this video a like and subscribe.